In this video, we are going to discuss some basic algebra with complex number. The first of this is triangle inequality. So we will discuss about the triangle inequality first. Triangle inequality. So what is the statement of a triangle inequality for complex numbers? Obviously. So if Z1 and Z2 are two complex numbers, then Z1 plus Z2 modulus is less or equal Z1 modulus plus Z2 modulus. So this is the basic form of the triangle inequality for complex number if Z1 and Z2 are two complex numbers. So we need to prove this inequality. But before going to the proof of triangle inequality, we need some other proof as well. So the first one is basically if Z is any complex number from the complex number set C, then modulus of Z is greater or equal modulus of real part of Z, and modulus of Z is greater or equal modulus of imaginary part of Z. So at first we will prove this inequality. So as Z is a complex number, it has a basic representation like x plus iy in the 2D coordinate system. So modulus of Z is basically the distance between the origin and the point in the 2D coordinate system. So this will be something like root over x square plus y square. So from here we can say that modulus of z whole square is basically x square plus y square. But x is the real part of z and y is the imaginary part of z. So we can write it as real part of z whole square plus imaginary part of z whole square. So from this equation, let's say this is equation non star. So from this equation, we can say that, or we can see that this is non-negative because this is representing modulus of a complex number and its square. And obviously, real part of z square is also non-negative. Imaginary part of z square is also non-negative. So from here, we can write down the inequalities as all as z square, real part of z square, and imaginary part of z squares are non-negative. So we can write it down as modulus of z is basically z square is basically greater or equal real part of z square, and modulus of z square is greater than imaginary part of z square. So from here we can write it down as modulus of z is basically real part of z modulus, and modulus of z is greater or equal modulus of imaginary part of z. So hence the proof is completed. So we need these inequalities to prove the triangle inequality later. Next, move to the second one. If z1 and z2 are two complex numbers, then z1 plus z2 modulus square is equal to z1 modulus square plus z2 modulus square plus 2 times real part of z1 and z2 bar. That is the conjugate of the complex number z2. So how can we prove this? prove this equality, we need the concept of or the need the properties of conjugate of a complex number and the modulus of complex numbers. So from here, let's start with z1 plus z2 modulus square. So we know a basic properties of modulus, that is if z modulus square, if z is a complex number like x plus I y, then we can write down z modulus square as z times the conjugate of z. So using these properties here, we can write it down as z1 plus z2 times z1 plus z2 modulus. So now we are going to apply the property of conjugate of two uh, complex numbers, that is z1 plus z2. So from here we can just simply verify that if z1 is something like x1 plus iy1, then if z2 is something like x2 plus iy2, then conjugate of z1 plus z2 is basically z1 conjugate plus z2 conjugate. So this is another property of conjugate of complex numbers. So from here we can write it down as z1 plus z2 times z1 bar plus z2 bar. So from here, after multiplying each of the terms, we will get z1, z1 bar plus z2, z2 bar plus z1, z2 bar plus z1 bar, z2. So again, using this property, we can write it down as z1 modulus square, and we can write it down as z2 modulus square plus z1 z2 bar plus z1 z2 bar whole bar. So again, using the properties of complex conjugate, we can write it down as this. Also, we have the property z1 bar is basically z. Double bar on z is basically the complex number z. So we are just using these properties here. So from here, z1 modulus plus z square plus z2 modulus square plus 2 times real part of z1 z2 bar. Here we are also using some properties of conjugate of a complex number, that is if z bar is the conjugate of a complex number, then z plus z bar will cancel out the imaginary parts, so it will be 2 times real part of z. So we are just writing down these properties from these two. So hence our proof is completed. So we have this equality and we have these inequalities. So using these two, we will just prove the triangle inequality now. So the statement is prove the triangle inequality for complex numbers. So from the proofs above, we can use the second result first, that is z1 plus z2 modulus square is basically z1 modulus square plus z2 modulus square plus 2 times real part of z1 z2 bar. So we know one property like z modulus is basically greater or equal real part of z modulus. So we can write it down as z1 plus z2 square is basically z1 square plus z2 square plus. So from here we can see that this real part of this, but if we just replaced it with something like this one, so what will happen? So just our equality will be gone, and this will be replaced by some less than or equal inequality. What will happen? It will be just 2 times z1 z2 bar modulus. So we are just replacing this part with this part, and obviously this part is greater than this part, so we can just simply use it here. Okay, so from here z1 plus z2 modulus square is basically z1 plus z2 square plus 2 times z1 z2 bar. So here it will be equality, sorry, still this is basically. So here we are just applying this property, that is modulus of z2 bar is basically equal to modulus of z2, and also modulus of z1 z2 is basically modulus of z1 times modulus of z2. We can just we already proved this theorem, because if two complex numbers are multiplied by one another, so their modulus will be multiplied and their argument will be added. So from this property we can easily prove that if z1 and if the modulus of z1 times z2 will be the multiplication of their individual modulus. So from here we can say write down z1 plus z2 modulus square is basically less than or equal z1 plus z2 modulus whole square. You can see that all the terms here are modulus. That means all the terms here are non-negative. So we just can do the square root. So if we just do the square root, it will be something like z1 plus z2 is less or equal z1 plus z2. So yes, this is our beautiful triangle inequality, and hence the proof is completed. So we can also prove this by this geometrically. So we know that for any real number, uh, if we consider a triangle, so if we consider a triangle with sides A, B, and C, then the sum of any two sides, that is any two sides, let's say A plus C will be greater or equal B, and A plus B will be greater or equal C, and B plus C will be greater or equal A. So sum of any two uh, sides of the triangle will be greater than the third sides. So as we can represent the complex numbers z1, z2, and z1 plus z2 in Cartesian coordinate system. So what will happen? So let's say this is our complex number z1, and this is our complex number z2. Then what will be z1 plus z2? So if we just place this z2 here, so if we just place the z2 here, then we can form a parallelogram, and the diagonal of that parallelogram will be our z1 plus z2. So this length will be modulus of z1, this length will be modulus of z2, and this length will be modulus of z1 plus z2. So we, again, from here we can also say that, okay, obviously z1 plus modulus of z1 plus modulus of z2 is going to be greater or equal z1 plus z2. So the equality hold if z1 and z2 are exactly the same numbers. That is, if z1 is equal to z2, then z1 plus z2 is basically equal to z1 plus z2. So the equality holds only for this case. So we can extend this triangle inequality in the more general form, and the general form can be written as z1 plus z2 and up to zn. Modulus of this whole term will be less or equal z1 modulus plus z2 modulus and up to zn modulus. So this is the more general form. We can just prove it using the method of induction, because we have the base case, that is z1 plus z2 is less or equal z1 plus z2, and then we can use the method of induction to prove that. So the proof is basically left for an exercise. So you can use proof by induction. We already know that the base case is true, so obviously we just need to check that if the case is true for n, then it will also be true for n plus 1. So you can just easily prove the form from here. Next topic is going to be nth root of complex number. So let's say z0 is our given complex number. So z0 is basically our given complex number. And we are going to find out the nth root of z0. That is, our goal is to find z0 to the power 1 over n. Here n is any natural number, that is n can be 1, 2, 3, 4, 5, 6, anything, but basically if the values of n is 1, then this is not exactly the root. This is basically the values of z0. So here n is basically greater or equal 1, and obviously n is a natural number, and n belongs to natural number set. So we want to find out the nth root of z0. Here z0 is a complex number, so we can assume z be the nth root of z. So as z is the nth root of z0, so we can write it down as z is equal to z0 to the power 1 over n. So from here, after raising the power to n, we'll get z to the power n is equal to z0. Now z0 is our given complex number, so we can obviously transform it into polar coordinate form. So the polar coordinate form of z0 is basically r naught e to the power I theta naught. Z is our nth root of the complex number z0. Then it has some polar representation as well, so it will be r to the power I theta. So after substituting them here, it will be r e to the power I theta to the power n is equal to r naught e to the power I theta naught. But we know that this representation and r e to the power I theta naught plus twice k pi are basically representing the same complex number, just because if we are just going clockwise or counterclockwise, um, twice by degree, or so twice by 360 degree, then we will get the same uh, complex number. So from here we can also write it down as r to the power n e to the power I theta to the power n r naught e to the power I theta naught plus twice k pi. Now, after applying the de Moivre's theorem here, we will get r to the power n e to the power I n theta r naught e to the power I theta naught plus twice k pi. So here two complex number in polar coordinate form. So if we just as this two complex numbers in polar coordinate form are equal, so obviously their modulus will be equal to each other. That is, r to the power n will be r naught. That means r is basically r naught to the power 1 over n, and n theta is going to be um, theta naught plus twice k pi. That is, theta will be something like theta naught divided by n plus twice k pi by n. So if we are going to look here, k can be any integer. It can be a positive integer, it can be a negative integer, in fact it can be neutral number 0. But here we are going to find out the nth root of complex number. So our goal is to find the nth root of a complex number. So we are basically concerned about n distinct roots. That means we are going to solve an equation, and then our goal is to find out n distinct roots. So how can we find this? We can just consider the values of k from 0 to 1, 2, 3, and up to n minus 1. And then we will get some different values of theta. And as the values of theta is different, so our roots will also be different. So the nth root of so z naught is, or sorry, this should be r. Nth root of z naughts are r to the power 1 by n, r naught to the power 1 by n, e to the power I theta naught by n plus twice k pi divided by n. Here the values of k is basically from 0, 1, 2, and up to n minus 1. So what will happen if the values of z1, z0 is basically 1? So z0 can be any complex number. So this is the more general form for finding the nth root for any complex number. But what if z0 is basically 1? So this is called the root of unity. So if z0 is equal to 1, then it is called the nth root of unity. So if the values of z0 is going to is 1, then it's called the nth root of unity. And obviously, as we can see, z0 is equal to 1. That is, in the polar form, z0 is equal to 1 is basically modulus is going to be 1, and then the argument is going to be 0. So from here, our nth root of unities will be um, e to the power I twice k pi by n, where k is going to be 0, 1, 2, and up to n minus 1. So using this property, we can easily find out the nth root of any complex number. It can be square root, cubic root, or eighth root, anything. So now our next topic, very important topic to be honest, is the matrix representation of complex number. So we're now going to discuss about the matrix representation of complex number. So what is the matrix representation? That means we can represent our complex number in a matrix form. So what will be that form? At first, consider r theta, that is basically represent a rotation of the 2D plane with an angle theta. So r theta is something that is rotate our natural coordinate system with an angle theta. That means, let's say this is our coordinate system. So there are some grids here. So let's say these are some grid points, some horizontal grids. As well some vertical grids. So this is our basic two-dimensional coordinate system. So what r theta is doing, r theta is basically transforming this coordinate system or rotating this coordinate system with an angle theta. Now we will basically visualize what will happen after applying r theta. So this is our initial coordinate system, and then after applying r theta is basically rotating our coordinate system with an angle by an angle theta. So our new coordinate system will be something like, let's say this angle is theta. So let's say this angle is theta. So r theta is basically shifting our coordinate system or rotating our coordinate system with an angle theta. That means our new grid points will be something like, so our new grid points will be something like this. So what r theta is doing, this is our initial 2D coordinate system. And r theta is doing a rotation by an angle theta, that is, it is rotating the coordinate system by an angle theta. So by default, by definition, it is a linear transformation, because obviously our origin is fixed. That is, as we are rotating with an angle theta, we are not replacing or transferring our origin. Our origin is fixed. In the previous coordinate system, our origin was still 0 0, and in the rotated coordinate system, our origin is still 0 0. And the thing is, all the grid lines are straight line. Our axis lines are straight line, and all the grid lines are straight lines. So intuitively, we can say that this r theta is a linear transformation. So this is a linear transformation or map. That means what is r theta doing? Let's say r theta is acting on a vector x, y. So for that, we need a basis. Let's consider the usual basis, that is the basis of the 2D coordinate system, standard basis. Standard basis for 2D. That is our 1 0 and 0 1. So r theta x times 1 0 plus y times 0 1, and then as this is a linear transformation, so x times r theta 1 0 plus y times r theta 0 1. Now we have to find out what is r theta doing with the 1 0 vector, and what is r theta, the linear map, doing with the 0 1 vector. So let's consider this in the coordinate system. So let's say our coordinate system is 2D coordinate system is something like this. So our 1 0 vector is basically this one, that is this vector is our 1 0 vector. So this is our 1 0 vector. So this vector is transformed by an angle theta. So that is, this angle is theta. So what will be the new coordinate system of that vector? So the new coordinate system of this vector is something like, if we just simplify this or take a perpendicular line from the vector, then this angle, this length is 1 unit. So this is basically cos theta. After applying some trigonometric identity, this will be sine theta. So our new position of the vector is basically cos theta sine theta. So after rotating by an angle theta, our 1 0 vector will transform into something like cos theta sine theta. And what will happen to the 0 1 vector? So let's say this is our 0 1 vector. So this is our 0 1 vector. So it will also rotated by an angle theta. So our new angle will be something like this new vector. So taking perpendicular line, and then we'll get, after some simplification, we'll get from here is y times minus sine theta cos theta. It's simple geometry here. So if we are just considering this thing, that is this axis theta, so this should be sine theta, and this height will be cos theta. So as we are considering sine theta in the negative axis, that's why this is going to be minus sine theta, and for positive axis, this will be cos theta. So our image of the vector xy is going to be this. So if we just write it down as a matrix rotation, then this should be something like cos theta sine theta minus sine theta and cos theta, and it is multiplied by the vector x y. Okay, that is basically came from an intermediate form, that is x cos theta minus y sine theta comma x sine theta plus y cos theta. Okay, so this came from this intermediate form. Basically, we get this matrix form from this part. Now, we are considering a theta angle rotation of the coordinate axis by a linear map. Now, we already know that z theta is equal 1 times e to the power I theta is also doing the same thing. That means if we multiply any complex number by z theta, then the new complex number will be multiplied by the modulus of the new complex number will be multiplied by 1, that is, it will stay same, and the argument of the complex number will be added by an angle theta. So z theta times x plus iy is also representing a theta degree a rotation. So that is z theta e to the power I theta times x plus iy. So e to the power I theta, by using the Euler equation, we can write it down as cos theta plus I sine theta times x plus iy. So after multiplication, it will become x cos theta plus ix sine theta plus iy cos theta minus I square y sine theta. So after separating the real part and imaginary part, it will become x cos theta minus y sine theta plus I times x sine theta plus y cos theta. So as you can see, these things and these things are more or less same, because we can represent the complex number x plus iy in as a single quantity in the 2D coordinate system as this. So this will be something like x cos theta minus y sine theta comma x sine theta plus y cos theta. Okay. So from here we can say that there is a relation between these two things, and more precisely we can say that the set of all such numbers, let's say if we are just represent this as z belongs to C, where modulus of z is basically 1, and all the set of 2 times 2 matrices that is representing a theta degree rotation, there is a connection between these two, and we can say that there is an isomorphism between these two sets. So more explicitly, we can write it down as r theta is basically, so the explicit the explicit isomorphism is something like cos theta plus I sine theta. We can write it down as cos theta sine theta minus, sorry, this should be sine theta and cos theta. That is what cos theta plus I sin theta is doing. This matrix is also doing the same thing. More explicitly, if we just break it down more, that is r theta is equal cos theta minus sin theta cos theta. So if we are just take the coefficient of cos theta, then it should be 1 0 0 1 plus sin theta times 0 1 minus 1 0. So this quantity is basically 1 and it is multiplicative identity. It's just because if we multiply any number, any matrix by this matrix, this will be exactly same, and this is basically behave like 1. And what is this thing? This thing is basically I, just because if we are taking I square, then 0 1 minus 1 0 and square, so this is basically minus 1 0 0 minus 1. So just if we compare with this, then this is minus 1. So from here we can write it down as r theta is basically cos theta plus I sin theta. So here's the basic or more explicit representation. Now, in general sense, let's say, for instance, z is not equal to 1, z can be anything. So what will happen? Z is not equal 1, z can be anything. So in general, we can write it down as a minus b, b, a is basically a plus I, b. And writing a complex number in this matrix form can also satisfy all the operation, that is addition, subtraction, multiplication, and division. In case of addition, adding to complex number means adding two matrices. Subtraction means subtract one matrix from another matrix. Multiplication means two matrix multiplication. Division means multiplication by its inverse. That means if Z1 and Z2 is multiplied, then their corresponding matrix, let's say M1, 2 times 2, and N 2 times 2 will be multiplied. And Z1 divided by Z2 means Z1, its matrix representation is M2 times 2, and Z2, its matrix representation is N2 times 2, but as we are dividing Z1 by Z2, so this should be M times N inverse. Okay. So these are the properties we need to, and all these properties are exactly same. So we can basically represent a complex number in a matrix representation like A minus B, B